Alrighty, welcome everyone. My name is Can and I am with Linkso. And today we've got Shilpa and Nick from the Master Gardeners presenting on an awesome topic. And if you have any questions throughout the talk, please feel free to type them in via chat where it says ask questions here, and we'll go ahead and address them towards the end of the talk. So we do have a couple hours, but I don't know if we're going to take the entire 2 hours with Q&As, but we'll see. Maybe we have a lot of questions. So welcome, Shilpa and Nick. I'll turn the class over to you both.
Thank you so much, Can. Welcome, everyone, to this presentation of exploring the connection between greenhouse gases and soil health. So I'm Shilpa Thanawala, and I'm here with my co-presenter, Nick Landolfi, and we're both UC Master Gardeners in the San Francisco and San Mateo counties. And special thanks today to Linkso Garden Materials for hosting us. And so I'd like to start by telling you a little bit about Nick and myself. Nick is a research immunologist and lifelong gardener who became a master gardener in 2018 upon his retirement from the biotechnology industry. He is a soil specialist, staffs the Master Gardener Helpline, and is a volunteer gardener at the Fair Oaks Adult Activity Center in Redwood City. He frequently lectures on soil science and best gardening practices, and he enjoys maintaining his vegetable beds, herb gardens, grapevines, and fruit trees, as well as caring for a Japanese garden with a koi pond. And I am Shilpa. I live in San Carlos, and I've been a UC Master Gardener since 2013. I enjoy growing herbs, fruits, and vegetables to use in cooking and baking. I have a small home garden into which I have crammed about 30 varieties of fruit trees, canes, and shrubs, a large herb garden, plants to support pollinators and beneficial insects, and California natives. I also volunteer in the Master Gardener Soil Specialist group, like Nick, and I teach classes on growing herbs, pruning perennials, and soil care. Now, a little bit about the Master Gardener program. The UCCE Master Gardener volunteers are trained and certified by the University of California to provide research-based information on home horticulture and pest management. Our goal is to help home gardeners and community organizations garden sustainably and create a healthy environment. So with that, let's get to our topic list for today. So today's presentation will be in two parts. So part one will cover an overview of greenhouse gases, or GHGs. We're going to see that abbreviation a lot today. So we'll talk about how the Earth's atmosphere evolved, what are greenhouse gases and how do they work, the effects of water vapor and positive climate feedbacks. We'll talk through the main greenhouse gases and their sources. We'll look at the serious impacts we're seeing of warming, and we'll go through some climate solutions that are being implemented now and for the future. Then in part two, Nick will describe the relationship between soil and greenhouse gases and how our practices at a small scale and a large scale can impact climate change. So he'll cover healthy soil and the carbon cycle, the benefits of increasing soil carbon, best practices to improve soil carbon sequestration, and the impact of plants on global atmospheric carbon dioxide. So let's go ahead and take a look at the phenomenon of greenhouse gases and how they work and the impact on our planet. So as we're all aware, we are living in a time of anthropogenic or human-driven climate change, and human activity has introduced a massive increase in the concentration of greenhouse gases in our atmosphere, which is increasing global surface temperatures. And it took us humans the past couple hundred years to establish the systems that are causing this. So we have systems established in the areas of energy and transportation, food and agriculture, our systems of production and consumption, our economic structures, and much more that are causing these problems. And so it may seem pretty daunting, but we can in fact change these systems, and we are. And I'll be talking about that a little later on. But first, let's take a look how Earth's atmosphere evolved over millennia to operate at a sustainable balance point, which is the environment in which life evolved on our planet, and therefore the balance point that life needs in order to survive. So let's go back in time to about 500 million years ago. And at this point, Earth's land masses started out as barren, dry, bare rock. Then, about 460 million years ago, the earliest land plants began to appear on Earth, and this happened in partnership with fungi. So today, we know that plants and fungi form partnerships. Many of us have heard of mycorrhizal fungi, for example. So it turns out such partnerships were taking place even at this early stage of evolution. Fungi allowed plants to get nutrients from the bare rock, while plants provided fungi with energy in the form of carbon-based compounds. And then by 400 million years ago, plants evolved vascular systems or roots to take up water. And plant roots and the associated fungi and bacteria then began to break down the rock, and Earth's crust began to change. So over the next few 100 million years, microbial species evolved to interact with living and decaying plants. And together, plants and microbes transformed Earth's mineral rock into carbon-rich soil. And this transformation allowed rainwater to infiltrate and be stored in the soil, collect in underground aquifers, move into creeks, rivers, lakes, and eventually back into oceans. And Earth's carbon-rich soil became a reservoir for water. So plants are instrumental in Earth's water cycle. Plants are also critical to the cycling of carbon through Earth's systems. And I'm not going to walk through this complex graphic right now, but I've included it so you can look at it more closely later. But for now, I want to highlight that plants draw carbon from the atmosphere through photosynthesis. So that's over on the left there. And soil microbes break down and cycle carbon. And then over time, carbon is stored or sequestered in soil. So Earth's atmosphere and biological life are closely interacting and have evolved together over the last few 100 million years. And so it's not by accident that we have just the right amount of carbon and water in the atmosphere to keep us warm. So now we're getting to the connection between these cycles and Earth's global surface temperatures. So how do carbon and water in the atmosphere keep us warm? And to understand this, we need to review the greenhouse effect. So how does Earth's atmosphere hold heat? Well, we start out with solar radiation hitting the Earth, and much of it is absorbed, but a portion is re-radiated as infrared heat, which is absorbed by certain gas molecules in the lower level of the atmosphere, trapping that heat near the Earth's surface. And these specific gases that have this property of absorbing that re-radiated heat are called greenhouse gases. And this is the definition. All greenhouse gases have this property of absorbing infrared heat. In contrast, we also have abundant oxygen and nitrogen gases that make up the bulk of our atmosphere, and they do not have this heat absorbing property, and so therefore are not considered greenhouse gases. So under normal conditions, and normal here means pre-industrial revolution conditions, there was a stable balance of gases from natural sources so that Earth's temperature was maintained at a consistent habitable level. Habitable here is a key word because we need the greenhouse effect to make Earth habitable. Without it, Earth's average global temperature would drop from our normal 57 degrees Fahrenheit to around 0 degrees Fahrenheit. And so that's really cold. Life would have evolved very differently, if at all, without the greenhouse effect. So before the 1800s, the balance of greenhouse gases had been stable for many millions of years. And so obviously that means some greenhouse gases come from natural sources. For example, carbon dioxide is emitted from the respiration of animals and plants, water vapor from evaporation and transpiration, again, involving plants. Methane comes from decomposition of organic materials. Nitrous oxide gets generated by soil bacteria. So all those are happening naturally. And then occasionally in Earth's history, there were periods of high volcanic activity, which would release a burst of greenhouse gases. And the period following that tended to be a little warmer, but would balance out over time. And so there were fluctuations, but they were small and within a range that kept Earth's global average temperatures stable. Now, looking at the right side, which is our current situation of rampant CO2, the industrial activities of humans have increased the concentration of greenhouse gases in the lower atmosphere, and that's throwing off this balance. And so today, because we've emitted more of those specific gases in our atmosphere, what happens is that more of Earth's re-radiated heat is being absorbed by greenhouse gases and retained near the Earth's surface. It's helpful to understand a little more about how greenhouse gases absorb energy because each gas in our atmosphere is a different chemical molecule and has different properties. So this chart shows how different greenhouse gases absorb energy at different wavelengths. So at the top up here, we can see that solar energy coming in has lots of radiation in the UV and visible light range, and that's based on wavelength of light, right? And we already know this actually, right? We know that there's UV light coming in. That's why we use hats and sunblock when we go outside. But once it is re-radiated and on the way back out, it's different. This re-radiated outgoing energy is of a longer wavelength that falls in the infrared range. Now, what the lower section here is showing is that each atmospheric gas absorbs radiation at different wavelengths. So the takeaway here is that carbon dioxide, this brown section, and this tea aqua colored water section, they both absorb a lot of energy right in that wavelength range that's being re-radiated from the Earth. So that re-radiated energy, which would normally escape, is being retained and absorbed by carbon dioxide and water vapor. And the more carbon dioxide and water vapor that we have in the atmosphere, the more energy that gets absorbed, and the more we cause increased global surface temperatures. So that's the mechanism. And of course, we see this very clearly from the data we have too. So we can look at the change in carbon dioxide levels and global surface temperatures together since the start of the Industrial Revolution, when humans began emitting carbon dioxide on an increasingly large scale. So this chart is showing data starting in around 1850 up through the present day on this x-axis. And then the blue and red bars on this chart are indicating the global temperature, and it's shown as a deviation from average over here on the left side y-axis. And then this solid line shows atmospheric carbon dioxide levels as they increase from below 300 parts per million to now, on this chart, which goes up to 2022, it was at 417. In recent seasons, most recently, we are at 425 parts per million and still rising. And that's on this right side y-axis. So we're seeing this very strong correlation, right? And in fact, scientists as far back as the 1850s have observed this, notably a woman named Eunice Foote, who first showed that carbon dioxide has that property of greenhouse warming. So this is very serious and it's not slowing down. But this graph doesn't show how severe this problem is. In order to understand that, we actually need to look at a much longer time scale. So this chart is showing data going back 800,000 years, much further back, right? And over all that time, carbon dioxide levels were stable, and they didn't exceed this 300 parts per million level. Now, recently, in a shockingly short period of time, humans have increased carbon dioxide levels dramatically, way above what was normal over the past 800,000 years. So for comparison, the last time the Earth reached where we are now, 400 parts per million of carbon dioxide, was a period called the Pliocene, 300 million years ago. And that's well before the times shown on this chart. So during that period, sea level rise was at least 30 feet higher than today, and much of the ice at Earth's poles was melted. Now note that the previous slide's chart is all in this straight up vertical portion of this graph. When we look at the time scale over that's shown on this chart, and this time scale is the time over which most current biological life, like modern humans, evolved. So this is truly a crisis. It's very serious and happening right now, and humans urgently need to make big changes in many of our industrial systems. But there is even a little more that we need to worry about here. So it turns out that as a result of the warming caused by the increased emissions of those greenhouse gases, we also get some secondary effects, and these are known as climate feedbacks. Climate feedbacks come in two types. If the feedback reduces warming, it's a negative climate feedback. And of course, that is helpful. We like that because it's reducing the warming effects. If the feedback amplifies warming that's already happening, it's a positive climate feedback, and that means that it adds to the original effect. And so these are the ones that are very concerning. So an example of a positive climate feedback is ice albedo. Albedo is a term from astronomy describing how reflective something is. So the way this works is that sea ice, which is white, reflects solar energy. As surface temperatures get warmer, we get melting of that sea ice, and that reveals more of the ocean surface. Now, that darker ocean surface absorbs more solar energy, and that leads to more warming, which in turn leads to more sea ice melting, and that in turn leads to more ocean surface being revealed, and so on. So you can see how that's a loop. And this effect is powerful, and we are losing sea ice at a rapid rate. So just like the sea ice albedo effect, atmospheric water vapor has a positive climate feedback effect. And the way this works is we have our current situation of increased greenhouse gases, which is causing warmer temperatures. And that in turn causes increased water vapor, increased evaporation of water from the Earth's surface. And this is because warmer air means more water vapor is held in that air. So basically, warmer air is going to hold more water vapor than cold air. So we all know this intuitively, right? Anyone who's hung out wet laundry on a warm day versus a cool day has seen that that laundry dries faster. So faster evaporation, more evaporation when it's warm. Okay, so that increased water vapor then absorbs additional heat because water vapor has greenhouse gas properties. And so the result is even warmer air temperatures because of that extra warming. And again, we're in a cycle that continues. It turns out that the warming we get due to human emitted carbon dioxide alone, so just what humans are emitting, that amount is doubled due to that positive climate feedback effect of water vapor. Now, if you look at just the quantities of atmospheric gases, water vapor is the most abundant greenhouse gas in our atmosphere. But remember that it's a part of the water cycle. Its maximum concentration depends on the temperature of that atmosphere. And when the temperature drops, water vapor condenses and cycles back out naturally. So, of course, the main thing we need to do to prevent this feedback effect is to reduce our greenhouse gas emissions and keep global temperatures low. But there's also a role for healthy soil to play here. And let's take a look at how that works. So now the water vapor in the atmosphere is part of the water cycle, and it interacts with our soil. And as this illustration shows, when we have degraded soil, compacted soil, and that's shown on this left side, that soil has low water holding capacity. And so that results in a lot of runoff and erosion. We get more floods, more drought. That compacted soil has very little pore space for water to infiltrate. That means that it's not supporting plant life very effectively. And that, of course, creates this condition where that soil surface is pretty hot, right? In contrast, if we have the situation on the right, which is the healthy soil and plant covered situation, right? Because healthy soil can support plant life. This soil has high water holding capacity. It shows good water infiltration, and that prevents that runoff and erosion. It's drought resilient, and we have lower surface temperatures in this kind of soil. So once again, we can improve how the water cycle operates by upgrading the way we manage our soil, and that's what you're going to hear about in part 2. Okay, so that's water vapor. It is a climate feedback effect, and we know that the answer is to reduce warming by reducing our emissions of human-generated greenhouse gases. So now we're going to shift gears and we're going to start looking at these greenhouse gases specifically. So here's a graphic showing the human-generated greenhouse gases. Carbon dioxide is, of course, our big main one, but there are others. We have 2 very powerful greenhouse gases of concern: methane, CH4, and nitrous oxide, N2O. Just like CO2, some methane and nitrous oxide production is natural and normal, and our industrial processes are producing a large excess of these. And as we'll see, they have a huge impact on warming. And then in addition to those, we have some industrial compounds that we group together under the name fluorinated gases. That is because they generally contain the atom fluorine. They're also abbreviated as F gases. These are not compounds that are produced by natural processes. They're solely human generated. And it turns out that this class of gases have tremendously potent warming effects. So each of the primary greenhouse gases behaves a little differently in terms of its impact. And we can sort of look at 3 different characteristics. One is that each gas is present in different amounts in the atmosphere based on what we're emitting globally, right? And in fact, here's a snapshot. This is from 2022, showing the proportions of atmospheric greenhouse gases. So around 80% carbon dioxide, 11% methane, 6% nitrous oxide, and 3% of these F gases, right? So different quantities. Then, in addition, each gas persists in the atmosphere for a different length of time. And so we're calling that the lifespan in our atmosphere. And then third, there's the efficiency of heat absorption. So each of these gases is a different molecule and has different heat absorbing capacity. So when we account for these 3 factors, we get an estimate of the global warming potential for each gas. Here's a table comparing lifespans and global warming potential for each primary greenhouse gas category, right? So we'll start with carbon dioxide. Now, carbon dioxide's lifespan in the atmosphere is pretty long, thousands of years, right? And then as far as its ability to absorb heat, we're going to use this as the reference. So we're setting that to 1 so that we can compare to it. So now if we look at methane, its lifespan is actually comparatively short. It persists for about 10 years in the atmosphere. And a key takeaway here is you can see how that affects the calculation of this global warming percentage. So when we calculate global warming percentage over 20 years, oops, sorry about that. When we calculate global warming percentage over 20 years, we get a pretty high impact. We get 80 times the global warming potential per ton compared with CO2. If we then take that potential over the next 100 years, it drops to about 30. So why is that? Well, that's because methane doesn't last that long in our atmosphere. So basically the takeaway there is that the short-term impact of methane is really large. If we look at nitrous oxide next, it has a 110-year lifespan in the atmosphere. So the projections turn out to be the same over the next 20 years as they are over the next 100 years because it's staying there, right? So the impact is not going to change over that time frame. Now, the important thing to notice with nitrous oxide is that every ton of nitrous oxide absorbs 273 times the heat that a ton of carbon dioxide does. That's huge. This is a huge impact, even more so than methane, right? And then we get a parallel story for the F gases. They persist for a while and they absorb even more heat, even more global warming potential compared to CO2. So the takeaway here that I want you to come away with is about the impact of these extra powerful greenhouse gases. And it works in 2 directions, right? Impact can be good if we act and not so good if we don't act. So if we don't reduce our emissions right away, these gases will cause very rapid warming. But reducing the more potent gases, greenhouse gases, can also have a huge impact right away, essentially put the emergency brakes on this warming and buy us time to make changes that take a little longer. So let's look next at what the sources of these gases are. So we'll start with carbon dioxide again. No surprise, the major sources are from the use of fossil fuels as our primary energy source in transportation, in our electric grid, our industries, right? In addition to what's shown on this pie chart, those of us who study how soil works know that another source is agriculture. So we have observed that there is data showing that prairie and forest soils hold more carbon than our farmland. And that is because our agricultural practices are causing soil degradation. And that lost carbon, when we lose that carbon, that stable carbon in the soil, where does it go? It ends up as carbon dioxide in the atmosphere. So that's not on this pie chart so clearly, right? Why is that? Well, the charts are showing the things that we're currently measuring. And as we get more sophisticated with the data that we can collect, our picture of the whole set of emission sources will also become more sophisticated. And then just a note here that the practices we use to manage commercial farms are going to filter over into residential gardening. So synthetic fertilizers, the use of biocides, and the practices that lead to soil compaction. So the changes we need to make on a large scale in the farming sector apply also to our home garden practices too. And so that is what you're going to be hearing about in part 2. Okay, so let's move to methane, our next gas. A notable source here is from organic matter in landfills. Now, some may know that California is now implementing SB 1383, and that's a statute that's aimed at reducing organic waste in landfills. And I've boxed things that relate to some of these practices that we can have impact on too as individuals, right? So organic matter in landfills connects to our efforts to compost. Oops, sorry about that. Yes, so, okay, continuing with methane, another big source is from confined animal feeding in the livestock industry. So that relates to our diets, how much meat and dairy we consume. And then, of course, methane is another name for natural gas. And this is 28%. So that is huge. And this comes from leakage, for one thing, in the delivery systems of the natural gas we use to cook and heat our homes, especially in California, because we're so reliant on natural gas here. It also comes from the petroleum production industry. There's a lot of sources of leakage of methane, and there's a big effort underway to get those under control because, again, methane has such a powerful effect. Next, we have nitrous oxide, as we saw, very powerful greenhouse gas. The main source, 75%, is from the wide use of synthetic fertilizers in agriculture. So when we use synthetic fertilizers in agriculture, a huge portion of what we apply is not used by plants. Some figures put that number at 80%. 80% of what we're applying, not used by plants. Some of that is leached into waterways and causes pollution. And then some gets converted in the soil to nitrous oxide by anaerobic bacteria. And that nitrous oxide then ends up in the atmosphere. So this is why it's so important to understand how to manage our agricultural soil and by extension, our home gardens as well. And Nick will be telling you about all of that in part 2. So now these previous 3, as we said, occur naturally. So nitrous oxide, methane, and carbon dioxide occur naturally as well. And it's humans that are adding an excess of these. Let's move to fluorinated gases. So this actually relates to something you might remember from a few decades ago. Those who remember the ozone crisis might remember the name chlorofluorocarbons, or CFCs. This is kind of they would fall into this category of gases. Now, it's actually a great success story that we took bold action under the Montreal Protocol decades ago, and we phased out those ozone depleting compounds. Really a good example of how action can have impact. The problem is that the compounds that we replace them with, those replacements are still very powerful greenhouse gases. Now, many of these compounds are used in things like refrigerants and coolants, fire extinguishers, pesticides, and aerosol propellants. So that's the stuff in spray cans. Those are some of these fluorinated gas compounds. And again, just to remind, they incur thousands to tens of thousands times more global warming potential per ton compared to carbon dioxide. So if we add all those greenhouse gas sources together on the previous slides, these are the percentages that the main sectors of industry are generating worldwide. And we know the sources for each sector, and there are multiple solutions that we can implement, and we're going to talk about that in a bit. And before we do that, though, let's look at some of the serious climate impacts that we're seeing and measuring. So this is going to be a visualization done by NASA researchers showing land temperature anomalies. In other words, how far off we are from the baseline average temperatures. So when we take temperature readings, how many of them are above average, over hotter than average, right? And how many of them are cooler than average? And in 1962, we start out with a pretty nice narrow bell curve distribution of the readings showing how temperature anomalies fall mostly, or how temperature readings fall mostly around average. And, the anomalies that we had are just, there weren't that many, and they were both hotter and cooler than normal, right? Okay. So now if we look at the visualization, we can watch what happens to that distribution of readings over time. And we get a little bit of variability as this goes, but we're starting to see that the whole curve is shifting over to the hotter side of the anomalies, right? Also, the distribution gets wider, right? Which that means that more of these readings are landing further off from average, right? And many more of them end up in this hotter than normal range. So it goes all the way up to 2022 and then it stops. Yeah, there we go. Oops. Okay, here we have another chart showing temperature trends from 1950 through 2022. 1950 down here, all the way through 2022. This was created by NOAA, and this is basically showing how ENSO affects global surface temperatures. Okay, what's ENSO? So we've all heard of El Nino, right? The technical term for that phenomenon is ENSO, which stands for El Nino Southern Oscillation. So that captures the El Nino effect and the opposite La Nina effect. Each of these bars on this chart corresponds to a month of temperature readings. The red bars indicate El Nino activity. The blue bars indicate La Nina activity. And back in 1950, if we look at this left side of the chart, the El Nino months were typically warmer, right? Above this average level. And La Nina months tended to be cooler, not 100% of the time, but in general, right? And then starting around 1975, 1980, all the readings start to be hotter than the historical average, and this continues to go up. And we see that the El Nino months are still a little warmer and the La Nina are still a little bit cooler, kind of generally, right? But the effect of ENSO is far smaller than the alarming overall trend of increasing global temperatures. So unfortunately, La Nina is not going to save us. The effect of warming is much bigger than that. Another impact we see is ocean warming. 90% of global warming is occurring in the ocean, causing the water's internal heat to increase. And heat stored in the ocean is causing its water to expand. And it's thought that that expansion is responsible for 33 to 50% of global sea level rise. And then in addition to that, we are seeing effects like coral bleaching and accelerated melting of ice sheets. We see intensified hurricanes and, of course, changes in ocean health and biochemistry. We can look at severe weather impacts. So, of course, happening globally. The data on this chart is just showing the US. And the way this chart is constructed is that this is a tally of severe weather events that incurred a cost over $1 million, right? And the bars, these stacked bars, are a tally of the number of events. So we start out in 1980, we go all the way up through this year, and every year the data is a tally of the number of events that happened. Now the stacked bars are color coded. So green corresponds to severe storms. We're seeing many more severe storms in the US that incur severe costs, right? The blue corresponds to flooding. So we do see an increase in the number of severe flooding events. Yellow corresponds to tornadoes, more of those generally. Wildfires are the orange ones, right? So that's really interesting to look at. Back in the 80s, all of these 80s, there were no wildfire events that incurred a cost of more than $1 billion. And then we start to see more of them in the 90s and a few more in the thousands. And then by the time we get to about 10 years ago, I think this is 2015, every single year there are $1 billion plus wildfire disasters, right? So the costs are increasing too. So that's what's shown on the corresponding to the right side y-axis, and that's the red and gray and black lines. Those are different ways of calculating disaster costs depending on the time frame. We see this peak in 2017, which was a disaster cost of $500 billion. Now, the way that climate change impacts are distributed globally is also very unequal. And so in the last few charts, we saw impacts like excessive heat and ocean warming, sea level rise, extreme weather. There's also things like pollution and air quality, water scarcity problems, food security is a huge one. We are facing a big crisis of biodiversity loss globally, and there are a variety of socioeconomic impacts as well. So to look at this, here is this striking graphic that was published in the New York Times in 2022. So I'm going to talk us through this. The size of each of these circles represents the relative amounts of greenhouse gas emissions that country has contributed since 1850. So these small circles mean not much contribution, right? We're going to see that each country's circle is placed along a vertical axis. What that indicates is its vulnerability, that country's vulnerability to climate change. And the researchers actually calculated a climate change vulnerability index. And the higher the circle is vertically on this graph, the more vulnerable that country is to climate change. So we start out at the very top with Somalia, a country that is expected to see very high climate impacts, but has contributed only a tiny fraction of emissions. And as we go along, we can move down this graph, right? And we see that up at the top, we have the lower income countries. We have many small island nations facing threats from sea level rise. We start to come to Pakistan and India, which are experiencing and will experience high levels of impacts. And we can keep going down this chart. And we start to come to the middle income countries. Now, these countries like China and Russia have contributed significantly to the greenhouse gas emissions, and they will see moderate impacts as well. And then as we continue, we come to the higher income countries. Now, this corresponds to a vulnerability index that's pretty low. So these now are the countries that are going to experience the least impact of climate change. But all the ones that are most responsible for emissions are down here, right? So The thing is that greenhouse gas emissions are closely related to industrialization, high energy use, transportation requiring fossil fuels, high consumption lifestyles, right? So these are patterns that occur in high income countries. And the result is that lower income countries are the most vulnerable, but the least responsible for climate change. And then we also have unequal generational impact. So climate effects have this time lag that's built in. And emissions from the past 70 years are now really showing up as life-threatening impacts, right? So all of these emissions from this time frame are now really showing up as impacts, right? And so what happens is that the impacts on your life will depend on when you were born. So children born in 2020 will face high temperatures over their entire adult lifetimes. And what this chart is showing that we have some options here. Our actions today are going to determine what people born most recently will have to go through. So that's what these different bars are showing. What, depending on the emissions scenario we end up following, the impacts could be extreme, this top bar, extreme heat, versus a low emissions scenario, if we make the necessary changes, that will result in just medium high heat. So we can make some choices that can really make a difference here. Okay, so we have looked in the last few slides at some of the really harsh realities we're facing, and it's normal to feel anxious, concerned, and maybe even a little bit hopeless about all this. And so thank you for sticking with it. And I want to shift now to the solutions that we have in front of us. So here's the picture I described. We have on the left the sources of greenhouse gas emissions. And on the right, we have natural carbon sinks. I'll describe what that means in just a second. And the task in front of us is to work concurrently to reduce those greenhouse gas sources, support carbon sinks, and improve society so that it's equitable for all. And so let's look at these sources and sinks more closely. So our greenhouse gases by sector, and hopefully you've started to notice, or maybe not, but I'll point out that the colors are going to be relevant as I go through the next slides with the solutions. Each of these sectors are consistently displayed in this color coding. So pay attention to that. And so the task is that we need to bring emissions in all these sectors to zero. And we have on the other side our natural carbon sinks. So what are carbon sinks? Well, we saw a quick view of Earth's carbon cycle, and Nick will explain that in more detail. But essentially, Earth's land and oceans naturally store vast amounts of carbon in stable forms for the long term, and those are our natural carbon sinks. And so we want to uplift nature's carbon cycle so that we can store more carbon in those sinks. Now, another thing to note here is that we have connections between emissions and soil. So the way we do our land use, the way we manage our land, including our farming practices and therefore our gardening practices, that's all part of the picture. And supporting land sinks is why we need to protect our forests and better manage our cropland soil. And so connecting this straight to part two, what Nick will be talking about, managing our soil to store more carbon, is really important because soil can be a powerful carbon sink. Okay, so let's get to the specific solutions in each of these sectors. So the way this chart works is that the size of each of these disks indicates the relative impact that that solution can have on reducing greenhouse gas sources. So let's start with our electric grid. Shifting production to renewables is the biggest circle on this whole slide. And that is because that is super impactful. That can cause a huge shift in our greenhouse gas emissions. We can also enhance efficiency. That particular solution shows up in a bunch of areas, right? We see that over in the transportation sector and in the building sector as well. Makes sense, right? Enhancing efficiency can help reduce emissions. So let's look at food, agriculture, and land use. The biggest disk here, the biggest circle here is this address waste and diets solution. Now, addressing waste, that's again related to methane production from landfills, the problem of biodegradable waste ending up in those landfills. And that's, of course, connected to our composting processes, right? And then the diets piece is the need to shift to plant-rich diets and the impact of methane in that area. Then there's also a solution that relates to changing our agricultural practices, again, changing how we manage our soil. And then this protecting ecosystems has to do with protecting areas like forests that are carbon sinks. And I'll also point out for our industrial sector, addressing refrigerants, right? Going to those alternative materials because of those F gases. So, and we could continue on. I'll skip ahead to the issue of land sinks because I'd like to point out that the biggest impact here is from shifting our agricultural practices, right? Huge potential impact. This is directly about our soil. So, and then we also have protecting and restoring our ecosystems. And a little side note here, we just saw this week some new research that came out just less than a month ago about trees. So we all know that trees absorb carbon dioxide, right? But this new finding by researchers is that they also absorb methane. This is amazing. We did not know this until this was the study was done. So we already knew that protecting forests and planting more trees is going to be important for reducing greenhouse gases. And that study shows how much more important it really is because methane, again, can have such a huge impact. Okay, so this is how managing our soil and ecosystems better can shift those sinks from greenhouse gas emission sources to being better as sinks. Here's a chart showing how specific solutions rank for big impact right away. So the top two up here are, of course, shifting to renewables. Not surprising, we already saw that. The next two green ones are about reducing food waste and shifting to plant-rich diets. We saw that already. I do want to point out this number 12 bar. That's kind of interesting. Peatland protection and re-wetting. So this right here, peat stores a great deal of carbon, and we want to leave those intact. And this is why we recommend that gardeners phase out using any peat-based products. So try to avoid peat. And it's not easy. You have to read the ingredients, right? Okay, then what I want to point out next is all these tan-colored bars. So again, that tan color is corresponding to our land sinks, right? What are these? Okay, so we've got restoring forests, right? Tropical and temperate region. We've got silvopasture. I had to look that up. I didn't know what it was. It is in fact a farming practice that integrates trees with crops and livestock all together. So there are agricultural practices that can enhance the land sink ability. Planting trees on degraded land, switching to perennial staple crops, tree intercropping. So what we notice about all these is that all these rely on healthy soil, right? Crops and tree planting are not going to succeed if we don't understand and update our soil care practices. Now, you might be thinking that all these solutions sound pretty expensive, maybe prohibitively so. But actually, it turns out that these solutions that we're looking at will save us money. So on this chart, this here is the zero cost line that's being shown, right? All the bars that extend below this line are solutions that are going to incur cost savings. The ones that go upward will incur costs, more expensive costs, right? The thing to note here is how many of these solutions are actually going to save us money. So for the electric grid, right, the solutions we named, they come with switching to renewals, for example, they come with big cost savings. Same with transportation, this aqua color, right? The transportation sector, switching to alternate modes, can save us a ton of money. And then the land sinks, the changes we want to make to our soil practices and our planting trees and everything, all of that is going to save money. And mostly when I look over at the solutions that are going to be more costly, they are in the purple, right? And the purple corresponds to our building sector. That actually makes some sense that in the short term, it's difficult to upgrade our buildings. So this is very, very encouraging. What it means is that it's actually more expensive to keep these big systems the way that they have been. And in fact, the director of Project Drawdown, which is a nonprofit that did this analysis, the director, Dr. Jonathan Foley, calls this the best bargain in human history. And we get the best economic benefits by making these changes now. So just like saving for retirement, another way to think of this is that carbon has a time value, and climate change is a cumulative problem. So the way to think of this is we can look at how the carbon, we can look at the carbon we've been emitting for the past 50 years, and that's this red curve, right? Since if we look at back over the last 50 years or so. And we know that carbon dioxide stays in the atmosphere for a long time. So just like a bank account, carbon dioxide is accumulating in the atmosphere. And we can think of that as the area under this red curve. For those who remember calculus, that's the integral. But it works the other way too. If we stop emitting and change that red curve to a downward trend, right? By taking the actions we just saw, we can avoid emitting what we would have. So that carbon dioxide that we didn't put into the atmosphere is what we're looking at now. So this is the trajectory we're on, right? And this is what we can do by taking those actions that we saw, right? And the difference is also an integral that represents the carbon that we didn't put into the atmosphere, which represents warming that we prevented. And what's great about that is that we can prevent that warming every year from now on by making those changes as soon as possible. So imagine that we shut down a coal power plant permanently today. We avoid putting that power plant's emissions into the atmosphere for the rest of the time that that plant would have operated. And so that has year-on-year effects, right? Sometimes we have multiple effects with an action we take. So if we look at deforestation, if we prevent deforestation today, we prevent those emissions from burning the forest, first of all, right? And then we also gain the benefit of that carbon sink for decades to come. And I mentioned deforestation because deforestation accounts for 10 to 11% of global emissions. And that is a huge percentage. You can compare that to the entire US economy, which is responsible for 10% of global emissions, right? So it's the same as that. It's that big of a deal that it's the same as the entire US economy. So the sooner we cut greenhouse gas emissions, the bigger the impact. And when this analysis is done, what's found is that emissions cuts are 96% of the answer. And that 76% of that has to be done in the next 10 years. So these big systemic solutions may seem really daunting, and it may seem like there's not much we can do as individuals. Now, of course, we need to be careful, right? We don't want to let powerful groups like fossil fuel producers continue to prevent necessary changes. And it's worth remembering here that the term carbon footprint was invented by British Petroleum, BP, which is a major fossil fuel producer. And they put it out as a marketing tactic to shift public perception of responsibility away from their industry. And so we don't want to buy into that narrative, right? We know better. But how does systemic change happen? Well, in some cases, change happens because technology and economic forces affect policy and culture. So great examples of this are the fact that solar and wind energy are now cheaper than fossil fuels. And that's driving systems change. For example, the massive solar arrays that are taking shape in Texas, right? Texas is becoming increasingly a place where solar energy is a source because it's cheaper. Obviously now, one person or family isn't going to single-handedly cut emissions, but if many individuals act, that cumulative effect does matter. And we need to remember that systems do work at all levels, right? Individuals are part of systems, can affect and shape systems. Individual actions can affect the community, and that in turn can affect the state, national, and international systems, right? And additionally, individual actions can send a powerful signal to markets, to policymakers, and to your friends and neighbors. So think of the first person on your block to install rooftop solar or start driving an electric vehicle, right? Every person who makes that change makes it feel more normal to the people around them. And it also sends a demand signal to companies. And so those early adopters, or early adopters, if you are one, you're driving broader implementation of these changes. Now, here is a chart on this page, and I know that the type is really small. I'm going to fix that in a minute. This is a chart showing the top 20 high impact climate actions that households and individuals can take, right? And so here's a magnification of the top 8 or so. This link down here has the whole list, so you'll be able to access that later. And you've seen some of these solutions already, but this is more specific maybe. The key thing here is that individual and household actions taken together have the potential to produce roughly 25 to 30% of the total emissions reductions needed to avoid dangerous climate change. That's huge, right? A quarter to nearly a third of the total emissions needed. So, what else can we do? Well, it's worth pointing out that humans generally feel better psychologically when our day-to-day actions align with our core values. We can also do things like continue to talk about climate to family, friends, neighbors. It's worth keeping it top of mind, right? We can endeavor to support companies that have better practices and that are upgrading their practices. Or conversely, if you find out that they don't support or they don't implement good practices, contact them to advocate for change because customer voices have influence. The overall goal with all of this stuff around individual action is progress, not perfection. And that is what we need to focus on. And when we do take action, there is real impact. So you may have heard of the IPCC, that is the Intergovernmental Panel on Climate Change. They convene regularly and they produce reports on the state of action on climate change. So on this chart, these lower curves represent how different action scenarios are going to reduce emissions and the amount of warming that we'll see by 2100 under these various scenarios, right? That's what all that is about. This red line up here, though, is worth noting because this represents what the IPCC reports were predicting from 10 to 15 years ago. So back then, the projected warming by 2100 was to 4 degrees Celsius. That is catastrophic, right? And because we have put policies and action in place here, we've dropped that projection to 2.5 to 2.9 degrees Celsius. So that's actually a very effective demonstration that what we do matters, right? That's a huge change. And it's worth noting that US emissions have dropped to 20% since 2007, while our economy has grown 36%. In the UK, emissions are lower today than in 1897. You'll also find hopeful stories in the news all the time. Here's just one example from South America. The city of Medellin, Colombia, had undergone rapid urban expansion, and the urban heat island effect was impacting residents, and the city had become significantly hotter than the surrounding areas. So the city took action. So they installed what they named green corridors in 2016. And that's what's being shown. This map here shows all the locations of these green, these routes that connect that have a lot of plantings in them, right? And then this picture here is showing a vertical wall garden that on a building that houses City Hall in Medellin, Colombia, right? And so what they did is they started with 120 individual plants and 12,500 trees. They continued to add from there. They chose particulate absorbing plants so as to improve the air quality for city residents. They also chose species that would provide food and habitat for wildlife. And the results that they got were really striking. They were able to see 2 degrees Celsius of cooling over the first 3 years after this was done, right? This is a great example of local action resulting in meaningful change and improving the lives of the residents there. So as we close out part one, we've reviewed how greenhouse gases work and what some of the emission sources are. We've seen some of the dire impacts of climate change, and we've looked at what we can do, and we've seen that we have quite a few answers, right? And we've seen what some of those top solutions are and their potential benefits. We've looked at some individual actions that can play an important role, and we've seen that there are reasons to be hopeful about all of this. And I'll just close by saying that we noted that many of the solutions to reduce greenhouse gas emissions depend on our soil management practices. And with that, I will hand it off to Nick for part two. Is soil the answer?
Thanks, Shilpa. Shilpa has given you a comprehensive introduction to greenhouse gases. She's explained the characteristics of these gases that lead to global warming and thus climate change, and identified the main players: carbon dioxide, methane, and nitrous oxide. She has mentioned the involvement of soil in the climate change quandary. I would like to expand upon the relationship between soil and atmospheric carbon dioxide and explain how your actions in the garden can have a beneficial effect on the greenhouse gas predicament. There is a critical relationship between soil and greenhouse gases. It operates on many levels, but the two main connections are shown on this slide. Soil captures CO2 from the atmosphere and stores it as soil organic matter. Conversely, soil can actually be a source of greenhouse gases, specifically carbon dioxide, methane, and nitrous oxide, which you now know are key players in global warming. While I'm saying soil, it is actually the life in the soil, including plants, that is really responsible for these activities. But importantly, soil acts as the indispensable setting in which these actions occur. Before we get to the specifics, I would like to remind you of the composition of soil. This pie chart shows the makeup of a typical soil. Soil is a combination of minerals, organic material, and air and water in the approximate percentages shown on this slide. About 50% of an ideal soil should consist of the pore space, which is occupied by roughly equal amounts of air and water. Most of the remaining portion of the soil, or about 45%, is made up of minerals contained in the three components of soil: sand, silt, and clay. Finally, the soil should contain 3 to 5% organic matter, although in many cases there is much more. Be aware that there are many different types of soil, and these percentages are variable. I should also explain the difference between soil organic matter and soil carbon, as these terms are often used interchangeably. Typically, about 58% of soil organic matter is carbon. Organic material is key to the functioning of the soil. Soil organic material includes recently added plant and animal residue that is in the early stages of decomposition. For example, decaying leaves, roots, and dead soil life. There is also this same organic material that has been extensively decomposed and is in a more stable form. Importantly, soil organic carbon also contains the entire soil micro and macrobiome, including bacteria, fungi, protozoa, as well as nematodes, earthworms, insects, and all other soil life. This soil life is collectively referred to as the soil food web. This is a tiered system of organisms that is essential to the decomposition of organic material and nutrient cycling. Each tier provides nutrition for the next tier. This is the basis of the soil activity I will describe. To appreciate the association between carbon dioxide and soil, you should have a basic understanding of the carbon cycle. The carbon cycle simply refers to the rotation of different forms of carbon through the various reservoirs. These reservoirs are the lithosphere, the atmosphere, the biosphere, and the hydrosphere. Today, we are only going to discuss the movement of carbon between the atmosphere and a portion of the lithosphere, specifically the soil, and a portion of the biosphere, specifically soil life. Let's focus on that portion of the carbon cycle. This diagram depicts the carbon cycle exclusive of human activity. This normal cycling removes carbon dioxide from the atmosphere through the photosynthetic activity of plants, which turns it into organic carbon. This carbon cycle can roughly be divided into two: a slow carbon cycle and a fast carbon cycle. The slow carbon cycle takes carbon dioxide from the atmosphere and sequesters it in very stable forms of organic carbon. This consists of the remains of plants and animals degraded, buried, and preserved in sedimentary rocks or geologic formations. This form of carbon includes fossil fuels such as coal, oil, and natural gas. Carbon in this category is sequestered for a period ranging from centuries to many millennia. The fast carbon cycle is the rapid cycling of carbon between plants and animals. In the soil, carbon dioxide is incorporated into plant material that decays into the soil or is consumed by animals, which then use respiration to digest the material to generate energy and release CO2. This cycle can happen in weeks or months. Here is the contemporary carbon cycle inclusive of human activity, which you can see on the far right of the slide. Human activity includes the combustion of fossil fuels, industrial processes, and all the other activities that Shilpa has described that release carbon dioxide into the atmosphere. Burning fossil fuels moves carbon from the slow carbon cycle, where it has resided for many hundreds of thousands of years, to the fast carbon cycle. The fast carbon cycle cannot naturally handle this excess carbon dioxide. This leads to an increase in the concentration of atmospheric carbon dioxide, which you now know will amplify the greenhouse effect, causing global warming and subsequent climate change. So you see, natural existing processes remove CO2 from the atmosphere and move it into the soil, thus reducing a key greenhouse gas and potentially alleviating global warming. There are advantages of increasing soil carbon in addition to reducing atmospheric carbon dioxide. Higher soil organic matter levels improve soil structure and enhance the activity of soil life, which boosts overall fertility. Also, increased soil carbon increases the water hold capacity of the soil, which is a very desirable quality. This critical connection between the soil and atmospheric CO2, coupled with the enormous capacity of soil to sequester carbon, suggests that a focus on soil is a viable strategy for mitigating climate change. As an educated gardener, you can take measures that both increase carbon sequestration in your soil and decrease carbon release back into the atmosphere. How do you do that? Let me give you some specifics, many of which you may already be aware, but I do feel they're worth emphasizing. Here are some things you can do to increase carbon sequestration in your soil. Composting, adding organic material, leaving roots in the ground, employing cover crops, rotate and diversifying your crops, growing perennials, avoiding chemical fertilizer, and proper water management. Let's go over each of these in a little more detail. Create and use compost. Compost your kitchen scraps and garden waste. This will produce a carbon and nutrient-rich material that you can add to your soil. When you compost these materials under aerobic conditions, where oxygen is present, there is some carbon dioxide released, but there is also significant carbon incorporated into the compost and the microbes responsible for the degradation. Now, as Shilpa mentioned, since the passage of the Mandatory Organic Waste Collection Act in California in 2022, it's actually forbidden to put any organic waste in your regular trash. The rationale behind this regulation is based upon limiting greenhouse gas emissions. Organic material in the regular trash stream will become buried in a landfill where it will degrade, but under anaerobic conditions, no oxygen. The bacteria that degrade organic material under anaerobic conditions release methane, which you know is a potent greenhouse gas, along with hydrogen sulfide and a small amount of CO2. So never put organic waste in regular trash. Either compost it yourself or put it in the garden waste bin. In addition to adding compost to your soil, the addition of any other organic material is beneficial. For example, organic fertilizers boost the nutrient level of the soil, which will enhance microbial activity, sequester CO2, and help build soil structure. Another important activity you can implement is to leave the roots of unwanted or dead plants in the ground. These roots will decay naturally over time, providing the soil life with a source of nutrition. Here's an example. The top portion of this photo shows the roots of a tomato plant that was pulled up at the end of the growing season. The bottom portion shows what is remaining from a similar plant that was allowed to stay in the ground over the winter. As you can see, the roots have decayed, adding organic material to your soil and leaving just a stub of material from the root crown. When you remove plants from the garden, simply cut them off the soil surface. This is a very easy way to add organic material to your soil. I will tell you that years ago, at the end of the growing season, I used to pull up my tomato plants, pound the root ball on the surface of the soil, and toss them into the garden waste. After I learned about soil, I realized I was damaging my soil in at least 3 ways. Number 1, I was removing organic material that was perfectly integrated into the soil and tossing it away. Number 2, I was removing any soil life that was associated with those roots, bacteria, fungi, protozoa, and also removing that from the soil and discarding that. And third, I was making a small crater in my vegetable beds, which now exposed the soil to sunshine and air, and that would accelerate degradation of what was previously covered organic matter. When you remove plants in the garden, simply leave the roots in. This is a very easy way to add organic material to your soil. The use of cover crops is also a very easy means to increase soil carbon sequestration. Cover crop is simply a crop grown solely to improve the soil. Purchase and plant cover crop seed mixtures, and most seed companies now sell these. Let the cover crop grow, and before it goes to seed, cut it down, leaving the stalks and leaves to degrade on the soil surface. Gardeners refer to this as chop and drop. You can sprinkle compost over this material to accelerate the degradation. This is very beneficial to your soil and much better than leaving the soil fallow. Another favorable strategy is to rotate and diversify your plants. Each plant is somewhat unique in the exudates it's added to the soil and the soil life with which it interacts. Here's a raised bed in 2 different years. In the one on the left, you can see I have mostly peppers with some parsley in the corners and onions in front. In the back of the bed, there's a cherry tomato and tomatillo plant. The next year, while I still have peppers in this bed, it gets a lot of sun and I prefer to plant my peppers there. I also planted marigolds and zinnias around the perimeter, French melon as a ground cover, and I switched the position of the tomatillo and the cherry tomato. Your soil will benefit from such variability. Incorporating perennials such as trees, bushes, and other perennial plants is also helpful. These plants have root systems deeper than most annuals and add significant organic material to your soil. Here's a landscape with a few citrus trees, a small fig tree in the back, and it's surrounded by grapevines. Perennial plants with deep roots are beneficial to your soil. Importantly, you should avoid all synthetic fertilizers, pesticides, fungicides. These can disrupt the natural soil microbial activity that is essential to increasing soil organic matter. It's fine to use fertilizers, but use organic products. Finally, proper water management is important for increasing carbon sequestration. Remember, the soil is alive. Allowing it to dry out is very detrimental to soil life. And while admittedly these organisms do possess strategies to survive dry periods, ideally you want your soil life to always be thriving. Now let's talk about the practices that will decrease carbon loss from the soil. Because in some ways this is just another side of the same coin, there is a certain amount of repetition. These practices are minimize soil disruption, minimize compaction, use mulching, avoid chemical fertilizers, and maintain trees. Minimize disruption of the soil. Adopt a no-till strategy. Disturbing the soil will interfere with all the resident soil life and expose soil organic material to the air and sun, which can accelerate its degradation and lead to carbon release. Now, certainly there are times when you need to disrupt the soil. For example, putting in new plants, scratching compost into the top few inches of your soil. This is fine. I am referring to the wholesale disruption of your planting area. I will tell you that several years ago, I used to dig down 8 to 12 inches and completely turn over the soil in my raised beds every single spring. It looked great, and I thought I was helping my soil. I realize now how disruptive this was to the soil life and structure. Now, having said this, I want you to know that there are situations where extensive tilling is warranted. You may need to work organic material into severely compacted soil, but this should be a one-time exercise and not a regular routine. Minimize compaction. Remember, I told you that an ideal soil has about 50% pore space occupied by air and water. Compacted soil is much less air, possibly none, and it may have less water than ideal, as compacted soil inhibits water infiltration. If the soil is waterlogged, this can inhibit root growth and in fact drown roots and cause them to decay. The lack of sufficient air also favors anaerobic degradation of soil material, which you now know will release methane, and this is less than ideal. Here are things you can do to minimize compaction of your soil. Manage foot traffic. Everyone needs to walk around in their gardens, but you can take measures to prevent compaction. For example, use stepping stones or mulch to protect the soil. I have at least 6 inches of mulch covering pathways in my garden where there are no stepping stones. And when I walk on these paths, I can feel the mulch absorbing much of the force. You should also eliminate bare soil. Exposed soil is susceptible to compaction simply by the elements. A raindrop can hit the soil surface at 20 miles per hour, and such force over an extended period will compact the soil. Finally, incorporating organic material into the soil is important. Soil rich in organic material is much more resistant to compaction than is soil with little or no organic material. Generous use of mulch can decrease soil carbon loss. Wood chips, straw, leaves, even grass clippings can serve as a mulch. This will retain moisture in the soil, gradually decompose to add more carbon. This is a simple method. You've seen this before. Avoid synthetic chemicals. Chemical fertilizers disrupt normal microbial activity. This can favor microbial populations that release carbon dioxide into the atmosphere rather than incorporate it into the soil. There are multiple organic fertilizers. Use those. Now, there's another disadvantage to using synthetic fertilizers that isn't related to carbon loss, and Shilpa has already mentioned this. They can lead to the release of nitrous oxide, which Shilpa has mentioned is a very potent greenhouse gas. This slide shows a portion of the nitrogen cycle. I won't go into detail today, but suffice it to say that there are 2 reactions in this cycle, nitrification and denitrification, which naturally lead to the emission of nitrous oxide, usually under anaerobic conditions. If, however, there is a surplus of ammonium or nitrate-based synthetic fertilizers, the natural cycle cannot handle the excess, and the amount of nitrous oxide released into the atmosphere is much greater. Another reason to avoid synthetic fertilizers. And finally, another way to decrease soil carbon loss is to maintain your trees. Trees absorb a significant amount of CO2 from the atmosphere. Through photosynthesis, they incorporate this carbon into the biomass of the tree. A single tree can sequester about 1 ton of carbon dioxide over its lifespan. ChatGPT will tell you the world's forests are believed to absorb 7.6 billion metric tons of carbon dioxide per year. And that's about 29% of the global CO2 emissions from human activity. Now, I reminded you of several strategies you can use to either increase the amount of carbon sequestered in your soil or decrease the amount of carbon loss. But I want to leave you with an appreciation of how important plants and soil are to the atmospheric carbon dioxide levels. I want to show you a video that makes this point visually in a much more persuasive manner than I ever could verbally. You should understand that while we talk about the average concentration of CO2 in the atmosphere, and currently it's about 425 parts per million, it is in reality quite dynamic. I would like to show you a video produced by NASA that represents a supercomputer model of the atmospheric concentration of CO2 over the period of 1 year. Before I start the video, I want to orient you on what you will see. It shows a map projection of the surface of the Earth. The concentration of CO2 in the atmosphere is shown by the color gradations that correlate to the scale at the lower right of the panel, with red to magenta colors indicating the highest CO2 levels you will see. This scale spans about 20 parts per million, so the changes you will see are within this range. I also want to mention this model was created in 2006, when the level of CO2 in the atmosphere was 40 to 50 parts per million lower than it is today. The lower left will indicate the date, but I want you to focus on the map, specifically the northern hemisphere, and I will narrate the timeline. Let's start the video. You can immediately see that the atmospheric carbon dioxide levels are very dynamic. As we move from January to February and then into March, you can notice the level of red increases in the northern hemisphere, indicative of rising atmospheric carbon dioxide. This increase in atmospheric carbon dioxide continues, with the peak occurring around the end of April and early May. As we move towards the latter part of May, you may notice a transition of the red toward yellow, indicating a CO2 decrease. This decrease becomes clearer as we move through June. Let's pause the video. What is happening? In a word, photosynthesis. As the northern hemisphere warms, plants are sprouting, coming out of dormancy, trees are leafing out, and all are beginning to draw carbon dioxide out of the atmosphere through photosynthesis. You can see this photosynthetic activity has a measurable effect on atmospheric carbon dioxide levels. Let's restart the video. As we move through July and August, you can see the decrease continues, reaching a low toward the end of September. That 4-inch tomato plant you put in the ground in the spring is now over 6 foot tall, bushy, and decorated with many tomatoes, and has used atmospheric CO2 along with water and nutrients from the soil to get to this stage. As we move further into the cooler fall, the vegetation in the northern hemisphere decreases its level of photosynthesis, and with it, the amount of CO2 removed from the atmosphere. By November, the red is returning. I think you can guess where we are going to end up, right back where we started. You might think, well, what's the problem? We put carbon dioxide into the atmosphere and the plants remove it. Well, as Shilpa has told you, this is the problem. This graph shows that over the past 60 plus years, the concentration of CO2 in the atmosphere has gone from below 322 parts per million to over 420 parts per million today, an increase of about 30%. As you can see by the sawtooth pattern, it does decrease every year, but it rarely gets back to the level of the previous year. And thus, the average CO2 concentration continues to rise, and with it, the greenhouse gas effect of CO2. With that, I would like to conclude our presentation. I hope Shilpa has given you a better understanding of how and why greenhouse gases are contributing to global warming and thus responsible for climate change. And I hope I have given you an appreciation for the carbon cycle and the importance of soil in sequestering carbon from the atmosphere, as well as specific actions you can take as educated gardeners to increase carbon sequestration in and decrease carbon release from your soil. We would like to thank Lingso for this opportunity and you for your attention. We now have some time to entertain questions.
All right, we only have one question. So I'll go ahead and I'll shoot. So the question is, would you still recommend pulling weeds or just cutting them continuously?
I think it depends on the weeds. Weeds that spread by rhizomes, you definitely want to get as much of that out of the ground as you can. A simple weed that's just an annual, I think cutting it off at the root will be fine.
Yeah, great.
Okay, I don't see any other questions. Well, oh, there we go. Okay. Do you think adding compost down 2 inches is deep enough to mix into this clay soil to add microbes?
Again, it depends on the specific nature of the soil. Really, a high percentage clay, really compacted soil, the answer is no. You need to work it in much further. Normal soil, in reality, just putting compost on the surface of the soil over an extended period of time, that carbon will make its way into the soil through natural processes. In most cases, no one wants to wait that long. That's why scratching it in the first few inches, I think, is a good compromise.
All right. Well, those are all the questions. Well, hold on. They're coming in. um, are you aware of what large-scale farmers could do if they stopped using nitrogen-based fertilizers? Example in Iowa.
Shilpa, would you like me to take that?
Sure, go ahead.
I think uh, ideally limiting the use of synthetic fertilizers, as we mentioned in a number of scenarios, is 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 something that you want to work towards. What you need to do is replace that with more sustainable options. And some of this is going on. Some of this has been going on actually for decades. The use of cover crops, for example. Um, it doesn't completely replace the growth promoting activities that synthetic fertilizers do, but it's a step in the right direction. And I think some of the practices that are going on now are moving us into the right direction. Remember decades ago, people used to till their soil completely, leaving it exposed to the elements, possibly leaving it fallow over the winter, and then planting it in the summer and pretty much saturating the soil with some type of synthetic chemical fertilizers. We've come a long way since then, but we still have a long way to go.
Agree completely. And that's where some of the change that's happening. I think there are a lot of experiments going on with things like regenerative farming and switching our practices from adding these synthetics to even studies that focus on combinations of cover crops that result in more than the sum of the benefits of just one or two, right? So there's lots of studies going on, lots of change coming up. So yeah.
Alrighty. Have you had any experience in using biochar in your gardens?
Nick, you should take this.
I have not. I know it's somewhat controversial. The use is somewhat controversial. On paper, it seems to make sense. It's a somewhat inert form of carbon being added to the soil, but I don't have any practical experience with it.
I haven't tried it either. It is on the list of potential promising solutions. I think I believe I've heard of a couple of companies. I think there's one called Napachar that's experimenting with this. So, both the production and the use of it. So yeah, I think we're in the early days of that.
The folks are wondering what the controversy is.
Oh, Nick?
I think it's just unclear exactly what the potential benefit is. My understanding is that biochar basically it's something that's generated very high temperatures, degradation of organic matter under very high temperatures, the types of things that happen, for example, in forest fires naturally. This does seem to have somewhat a positive effect on subsequent regeneration of previously burned areas, but I'm unaware of any rigorous studies that have actually examined the true value of adding biochar to, for example, vegetable gardens.
Well, just to add on to the biochar controversies, one of the main things is the source for biochar. There are companies that use sewage sludge to make biochar, even though it's an inert product. That in itself is a huge controversy. So the source matters when you're making biochar. So I know that may be something that folks want to look into, the source of your biochar if you're using that.
Definitely.
Okay, so the next question is there a more energy efficient fertilizer than alfalfa pellets for nitrogen? How deep does alfalfa need to be dug in?
Mm.
No, there are a number of organic fertilizers that have N values equivalent to alfalfa. For example, blood meal, I think, does. And I think part of the difference is kind of the time frame under which they operate. I know Terry Linkso has told me that blood meal will make nitrogen available to plants much faster than will alfalfa. I hope I'm quoting her correctly. But yeah, I think that there are options, and I guess my best recommendation would just be trial and error. But to answer the basic question, yes, there are options which are equivalent in providing nitrogen to your plants. Just look for that N number.
And then I would maybe tack on to that, that when you're adding amendments like that to your soil or not, or sources of organic fertilizers, keep in mind that it's still a whole system, right? Whatever you add, it may or may not be taken up by the plants depending on the health of the soil biology that you have in place. So always keeping that in mind.
Alrighty. So the next question is, what is the best way to leverage our consumer dollars when we are purchasing food items to have the least negative impact on our planet?
Oh, okay, great. So one big cost that's incurred is where is your food coming from, right? So looking at, this is one of the things to look at. We certainly are very privileged in our communities, especially in the Bay Area, to be able to get almost anything we want at any time of year. But it's worth looking at, where did that come from? Was it shipped from South America? What were the transportation costs? There's a fossil fuel impact of transporting produce that was shipped from far away. That's one aspect you can look at. So how is that produced? There is the factor of how it's packaged, right? So thinking a little bit about how much plastic is being used in the packaging of your food. Again, you saw on those charts that I showed, when possible, choosing a higher proportion of plant-based foods, right? Because any animal-based foods incur a huge methane cost. What else? And then there's systemic things you can do, supporting local farmers, things like that, right? Who tend to use generally less of those industrial processes and are more operate in a more sustainable way. So and it's also easier to find out what are the practices that those farms are using, right? You can actually check on that if it's local and you know where it's coming from. So we're lucky. We have a lot of great farmers markets at least locally here in the Bay Area. And you can be quite in touch with the ways that your food is being produced.
Okay, so the next question is, what cover crops do you like for gardens and garden beds in the Bay Area?
Actually, I'm by no means an expert on that, but I do know the seed companies have matured, so to speak, in that they provide mixtures. And I should mention that mixtures are always best. In the past, people would just plant fava beans or vetch or a single crop, and that's no longer believed to be that desirable. A variety is much more efficient at sort of improving things. And I think that the best place to go for information is to look at the offerings from the various seed companies and see what they list for a particular mixture of cover crop seeds, what the end result is meant to address, and use that as your guide.
And
Yes.
I just, sorry.
Sorry, I just wanted to add a tiny bit to what Nick said. Yes to everything Nick said. Some of these seed companies, I've seen charts, really detailed charts of the benefits of each cover crop, the season. You want to pay attention to the season that you're planting it in. You wouldn't plant the same thing as a winter cover crop that you would as a summer cover crop. So the warm season versus cool season matters. Annual versus perennial matters, right? Because it depends on what you're going to do to terminate that cover crop. And then reinforcing what Nick said about diversity. I think the more recent studies have shown that you want a diversity of species and plant families in your cover crop mix. So one really lovely idea that I'm stealing from Lisa and Kathleen Putnam that had presented this years ago was it's really nice to take some key cover crop species and then mix in wildflowers, right? So you're getting lots of different species, lots of diversity. And what that does is improve the diversity of your soil life. And that's going to improve all of your biology, right? So even the mixes can be enhanced with adding more species, right? And it'll be prettier if you add wildflowers. So always a benefit. Go ahead, Ken. You had something else to add.
Oh, you covered it. I was just going to bring up Lisa and Kathleen's talk, which is available under our website too on cover crops. So if anyone's interested, you can check that out under Linkso's community resources page.
It's an excellent talk on cover crops.
Okay, so the next question is, what is the source of food waste, commercial or consumer, and how is that addressed from a policy perspective?
Okay, I don't have the breakdown at the top of, at my fingertips right now. Much of this is systemic, right? I mean, there is a food waste issue from consumers. I want to say that that's around 30% of the problem, and then the rest of it comes from the waste that is generated because some produce doesn't make the cut, doesn't look nice or whatever. You may have heard there are some companies that are trying to find a consumer stream for using up that slightly less pretty produce, right? We have in the US some expectations around how our produce should look. So yeah, a lot of these, I think a lot of it happens in the production process. Some of it happens, like at the grocery store level, that kind of thing too. So I don't have the breakdown, but yeah, a lot of it isn't necessarily at the home residential level, but some of it is, right? So it does, again, the aggregate of what we do in our homes does have some impact.
And to add on to that, a couple of years ago, the Senate bill just passed a 1383 that mitigates the diversion of food waste going from the landfill back to consumers in the form of compost. So do look that up if you're interested in more policies and how that's helping our community locally. So next question is, if the soil gets compacted, would you fluff it up and add compost?
The answer is yes. Working organic material into the soil, and then subsequently protecting that soil from further compaction is the best strategy. And this is one of those examples where wholesale tilling or disruption of the soil is warranted. Because what you have with compacted soil is not really something that you have to worry about destroying. It's pretty much already destroyed. What you want to do is get it back into a position where there is that 50% pore space. There is significant organic material. There is active soil life. And that may require extensive disruption.
Okay, that was our last question. We do have a few minutes. If either one of you want to do a closing remark and maybe give us one takeaway, if I know there's a whole bunch of statistics and data is presented today. So if we can take away one thing, what that would be, if you can share that with us, that would be great.
Well, I would say there's a power in the individual. I know we show you these charts and these global effects, but you can still operate independently to be in a manner that is consistent with the environment. And as more people do that, the bigger the effect will be. So I think I can echo something that Shilpa mentioned. Don't think that there's no hope, because there is.
Beautiful. Agreed.
All right. Well, thank you so much to both of you. This was a super informative talk, and this is being recorded or will be available under our website too. And I just want to thank everybody for attending the class today. And for those who missed it today, do watch it on our website. So it'll be up tomorrow. So thanks again to Shilpa and Nick. Thanks, everybody.
Thank you.
Thank you. Thank you, everyone.